Okay, we are recording. Today, I'm going to present the public key cryptography, or asymmetric cryptography, or two keys cryptography. So, private key cryptography is also known as the symmetric key cryptography or one key cryptography. Symmetric because we use the same key to encrypt and decrypt. One key because we have only one key. Now, the problem with private key cryptography is that we need a way to share the key. And sometimes you will never meet with the person. As I was telling you, for example, you open an account and you never agree a password with the bank. And we need a way to still encrypt the communication between your computer and the bank, no? So if we don't have a confidential media to share the password between the two parties, the private key cryptography or the symmetric key cryptography or the one key cryptography is not ideal because we need to share. Sometimes you will communicate with somebody that you will never see. So it's very difficult to decide on a common password, no? So the person can encrypt when it will send to you, and you can decrypt when we receive because you are using a symmetric algorithm and you are sharing a password. Okay, so there is a solution to that, which is called the public key cryptography or the two key cryptography or the asymmetric. Asymmetric because we use one key to encrypt and another key, a different key, to decrypt. So in public key cryptography, every entity have a pair of key. When we say a pair of key, we have a public key and a private key. So each user normally have the choice to generate its pair of key. And the public key is the one that I'm going to advertise. So I share the public key with the world. And the private key, I keep it for myself. So if somebody find my private key, I have problem. Okay, I should not let my private key unprotected. It should be very difficult from the public key to infer the private key. It should be almost impossible, which means that if I have a lot of computing power, I should have a hard time from the public key to infer the private key. Ways. The problem that I might use an attack that will take, for example, 3,000 years. So if it will take 3,000 years, it's useless. I'm not going to run this attack. I better use my computer in something different. Okay, so we do have a way to infer the private key from the public key, but it has to be very expensive at the computational level. So we can normally exchange the keys. So what you encrypt with the public key, you decrypt it with the private key. Or you can do the reverse operation. What you encrypt with the private key, you decrypt it with the public key. But most of the applications that we are going to see, we will use the public key to encrypt and the private key to decrypt, even if we can do the reverse operation. So there are two famous algorithms for public key cryptography. One is called RSA from three investigators from the MIT. Rivers, Shamir, and Adelman did this algorithm, their name is here, in 1977. And it is basically the most popular algorithm to generate public and private key cryptography. There is another one that was done by Taher El-Gamal, which is called the El-Gamal. And for example, PGP, Pretty Good Privacy, that was developed by the Free Software Foundation, the GNU, is one of these tools that you can use, and behind it have the Elgamal algorithm. So I'm going to explain the reverse Shamir-Adleman algorithm, the RSA algorithm. So the first step, we need to choose two large prime numbers. We are going to call them P and Q. So they need to be prime number, and they need to be large. Then we will compute what we call the modulus, and we will denote the modulus as n, and it will be the product of the two prime number, P and Q. And we will have something else that we call the totient. So phi of n will be P minus n times Q minus n. So we subtract 1 to the first prime number. We also subtract 1 to the second prime number. We multiply the result. And this will be called the totient. And I will denote it as phi. Then we need to choose E, bigger or equal to 2, that we will call the public exponent. And this E have to be coprime with the totient that we just computed. And there are some good value of when we say it have to be coprime, which means that the greatest common divisor between E and the totient have to be 1. So for example, you cannot divide both of them by 2 or by 3 or by 5 or by 7. The greatest common divisor have to be 1. So good value for E are prime number of this form, 2 to the power of k plus 1. So those are examples of good value of E, the public exponent. So let's say if we put k in 1, 2 to the 1 will be 2, 2 plus 1 is 3, and it's a prime number. If we put k in 2, 2 squared plus 1 will be 4 plus 1, which is 5, and it's a prime number. If we put k in 3, 2 to the 3 will be 9, that will be 8. 8 plus 1 will be 9. It is not in the list because it's not a prime number. Let's try the next one. If we put k in 4, 2 to the 4 is 16. 16 plus 1 is 17, and 17 is a prime number. Let's do one more case. If you put k in 5, 2 to the 5 is 32. 32 plus 1 is 33. 33 is not a prime number. It's 3 times 11. So we don't put it in the list as a good choice for the public exponents E. Then we will compute the private exponent D, such a way that the public exponent E times the private exponents D have to be congruent to 1 modulus phi of n, modulus the totient. Another way to write it is E public exponent times D have to be congruent to 1 modulus totient. Remember that the totient is P minus 1 times Q minus 1, where P and Q are two large numbers, and that have to be prime. So the public key will be a pair of integer. It will be the public exponent and the modulus. And the private key will be a pair of integer. It will be the private exponent and the modulus. Remember that the modulus n is the product of the two prime numbers. So now let's see how we will encrypt. So as I was telling you, most of the application to encrypt will use the public key. However, we don't need. We could use the private key to encrypt and the public key to decrypt. But most of the application is going to use the public key to encrypt and the private key to decrypt. So we will see how we encrypt if we use the public key. So let's say that we have a message, a plain text message that we want to encrypt. It will be an integer between 0 inclusive and the modulus exclusive, which is P times Q, the two prime number. So also the ciphertext will be an integer, also between 0 inclusive and the modulus exclusive, which is n. So when you give me a plain text m, I can go to the ciphertext using this formula. I will take m, which is the plain text, and elevate m to the power of e, the public exponent. And the result, I will compute its modulus n, which is the modulus, no? And this result will be the ciphertext. Now, if you give me the ciphertext C and the private key, which is a pair of integer d and n, I can go back to the plain text using this formula. So I take the ciphertext, I elevate it to the power of d, and I compute the modulus of the result with n. And this will be the plain text. So look, there is something that is important to understand. The strength of the RSA algorithm is based on the fact that it's very difficult to factorize big number. So remember that n is the product of two prime numbers. If you can factorize them, you can find the private key. The problem is how to factorize if I give you a big number with, for example, 1024 bits. And this big number is the product of two prime numbers. The problem is how to find P and Q. If you use, for example, 2048 bits for the modulus, inside the modulus, remember you have a product of two prime numbers, P and Q. It's very difficult to find P and Q. It takes many, many years. It will take 100 years, more than 100 years, if you have two prime numbers that are multiplied, and the result, the modulus, is 2048 bits. It takes a long, long time. We don't know how to do that because it's NP complex. It takes a long time. But if we did have the power of computing, we'll be able to factorize and get the two prime number. And if we have the two prime number, we can get the private key. And if we have the private key, we can decrypt. We have the public, we have the private key, we have all. Okay, so this is the problem. It is very, very difficult to recover P and Q, the prime number. Let's see an example. So instead of taking two big prime number, of course, if we take two big prime number, we are going to be lost in the calculation. So we are going to take two small prime number. So P is my first prime number. 3 is a prime number. So 2, 3, 5, 7, 11, 13, 17, 23, etc., are prime number, no? Q is the second prime number. So the first thing that I do, I compute the modulus. And the modulus is the product of the two prime number, P times Q. So it will be 3 times 5, which is 15. I will need this modulus, for example, to generate my public key and my private key. Because the public key is the public exponent and the modulus. And the private key is the private exponent and the modulus. So I do need the modulus. Now let's compute the totient of P and Q. So the totient will be P minus 1 times Q minus 1. So P is 3. 3 minus 1 is 2. Q is 5. 5 minus 1 is 4. So 2 times 4 will be 8. This is the totient. So now the steps say we need to choose a public exponent E, such as that the public exponent E and the totient, which is 8, are coprime. So any integer that will be coprime to 8 will work. For example, can I choose 9? What does it mean coprime? The only divisor that they have in common is 1. For example, if you take 9, is 9 coprime to 8? Of course they are coprime. You can only divide them by 1. So the greatest common divisor is 1. Why? 8 is 2 times 2 times 2. And 9 is 3 times 3. So if you want to divide them, you can just divide them by 1. So when they are coprime, it means that the greatest common divisor will be 1. Now, if I ask you 50, is 50 coprime to 8? No. Why? Because we can both divide them by 2. So the greatest common divisor is not 1, it's 2 in this case. So they are not coprime. I can divide 8 by 2, which gives me 4, and I can divide 50 by 2, which gives me 25. So 8 and 50 are not coprime. So I cannot choose, for example, E as 50. So possible value of E in this case will be what? Can I use 2? No. Can I use 3? Yes. Can I use 4? No. Can I use 5? Yes. Can I use 6? No. Can I use 7? Yes. Can I use 8? No. Can I use 9? Yes. Can I use 10? No. Okay? So here they took as the public exponent, they took 7. So 7 is a prime number. So 7 is just 7. When you try to factorize 7, it's just 7. And 8 is 2 to the power of 3, which is 2 times 2 times 2. So the greatest common divisor is 1. Once you choose the public exponent, you have to resolve one equation to find the private exponent, which is called D. And D must fulfill this equation. E, which is the public exponent, times D, we already choose the E, which is 7, times D, that we are looking for, must be congruent to 1 modulus the totient. And the totient is 8. So if I replace, because I already choose E, it will be 7 times the private exponent that I'm looking for, must be congruent to 1 modulus the totient, which is 8. So I need to resolve this equation. So value for D that are possible are this one, 7, 15, 23, 31. Let's verify. What is 7 times 7? If I do E times D, if I take D as 7, we already know that E is 7. So 7 times 7 is 49. 49 modulus 8 is what? 1. Why? What is 8 times 6? 48. So 8 times 6 plus 1 will be 49, which means that if D is 7, it's walk. Let's try 15. If E is 7 and D is 15, 7 times 15 will be what? 105, exactly. 105 modulus 8. So 104 is a multiple of 8. So 105 modulus 8 will be 1. So I can also use, for the private exponent, I can use 15. I can use 23. I can use 31. Any value of D that fulfills this equation is a solution. So let's say that we take the first value, 7. So our public key will be the public exponent, which is 7, and the modulus. Remember that the modulus is the multiplication of the two prime number. And the private exponent will be D, we just computed by resolving this equation, and the modulus. So look, I will make this public. Now, if somebody can find the factorization of that, the person have all the data. If some person can say, oh, 15 is 3 times 5, and find P and Q, this person can find the private key. What will happen that, of course, I'm not going to take 15. I'm going to take large number, because I'm going to choose two big prime integer. P and Q are going to be very big to make it very hard to the person to try to factorize them. But if the person can factorize them, unfortunately, the person can go back to the private key. So when you use a browser and you see the candle that show that things have been encrypted, we do use at the beginning this. We will see how. Okay, so let's see how we encrypt and decrypt. So we say that the public key is 7 and 15. Let me go back. 7 and 15 is the public key, and the private key is 23 and 15. So the private key is 23 and 15. So let's say that we have a message, which is 13, and we want to encrypt it. So what should we do? So it is there. We'll do 13 to the power of 7, modulus 15. So if I do that, let me show you with the computer. We are going to use our favorite calculator, which is Python. So Python 3, I need to do 7. I need to do 13, which is a clear text, to the power of 7. And the result of that, let me compute that, will be the number. I need to do it modulus 15. So the result is 7. So 13, the plain text 13, will become 7, as you can see here. If you give me a plain text of 3, I have to do 3 to the power of e modulus n. So 3 will become 12. So 3 will become 12, as you can see. Let's do 8. 8 will become 2. So let's do 8. 8 to the power of e modulus n, which is the modulus, become 2. So 8 become 2. Now let's do the reverse operation. From 7, I have to go back to 13. So let's decrypt. You give me 7, I want to go back to 13. So to decrypt, what we do is, you give me, for example, 7, I will elevate it to the power of d. D is 23. It's going to be a large number already. Okay? And this modulus 15. And look, the 7, we went from 13 to 7 when we encrypt, and we go from 7 to 13 when we decrypt. Okay? Let's see another one. For example, here we went from the plain text 3 to 12 as a ciphertext. And now let's see that we will go from 12 to 3. So I have a ciphertext, which is 12. I'm going to elevate it to the power of d, the private exponent, which is 23. It's a big number. And I have to do that modulus n. We call the modulus. And it's come back to 3. So 12, go back to 3. Okay, 12, go back to 3. So 3 went to 12 when I encrypt, and 12 go back to 3 when I decrypt. Okay. To do that, we need to compute what we call the modular multiplicative inverse. So the modular multiplicative inverse of an integer a is another integer b, such that a times b is congruent to 1 modulus n. So they are called inverse to each other, modulus n. Okay? For example, 8 and 7 are inverse to each other, modulus 11. Let's verify that. What will be 8 times 7? 56. And 56 is 11 times 5 plus 1. So if you take 56 and you do 56 modulus 11, it will be 1. Okay? So we can show that an integer a will have a multiplicative inverse modulus n if and only if the greatest common divisor of a and n is 1. Which means if they are coprime. If they are coprime, it means that there is an inverse of a modulus n. Okay? Okay, how we compute? For example, I have 8, and I want to compute the inverse of 8 modulus 11. How do we compute it? So look at what we are going to do. We are going to express 11, which is the modulus, in function of 8. So 11 is 8 times 1 plus 3. Then we are going to compute 8 in function of 3. So 8 is 3 times 2, which is 6, plus 2. Then we are going to compute 3 in function of 2. So 3 is 2 times 1 plus 1. When here we arrive to 1, we can go back. We stop doing that. Expressing number in function of other number. So now we can say that 1 is 3 minus 2 times 1. Okay, here you see it. Then we want to replace these 2 with these 2. So if I take the second line here, I can say 2 is 8 minus 3 times 2. So this 2, I replace it by 8 minus 3 times 2. So it will give me 3 minus 8 times 1 is 8. Negative will be positive. 3 times 2 times 1 will be 3 times 2. So then I will group the 3 together and the 8 together. So 3, here we have 3 times 1, and here we have 3 times 2. It's 3 times 3 minus 8. Then I want to replace, I can extract here 3 in function of 11 and 8. So 3 will be 11 minus 8 times 1. I'm going to replace this 3 by 11 minus 8 times 1. So times 3 minus 8. So 11 times 3, 8 times 3 minus 8. And this 8 times 3 and this 8 times 1 can be an 8 times 4. So this is what I got. Okay? If I change, I put the 1 on the right side and this on the left side, I have this. So since we are going to work modulus 1, and we have this left term is equal to this right term, that will be also true modulus 11. Now, modulus 11, I can suppress anything that appears like 11 times something, or I can add it. So here, for example, we decide to suppress it. And the other term, which is negative 8 times 4, we can write it 8 times negative 4. Then modulus 11, we can add any number of times 11. So for example, here I add 8 times 11. So you can suppress any time 11, anything that is 11 times something, or you can add them. Here we suppress it, here we add 8 times 11. When we factorize the 11, it will be, when we factorize the 8, it will be 8 times 11 minus 4. And 8 times 11 minus 4 is 7. So 8 and 7 are inverse. Modulus 11. So this is what we will have to solve in order to find the private key. So here we have some exercises. So the prime number is a little bigger. So let's do the exercise. So they said, let's assume that you choose as a prime number. You are going to choose 2 prime numbers, P and Q. So 13 is a prime number. 19 is a prime number. And they ask you to compute the public and the private key associated with P and Q. When I say the public and private key, I should not say the, because there is not one, there are several. We have several. So just give me one public and private key associated with this P and Q. So let's try to do it. For that, I'm going to start my Q is 19. Okay, so let's do things with that. So what should I do first? I need to compute what? The modulus. The modulus that we call n. And n is what? P times Q. So it will be 13 times 19. Okay, let's use the calculator to do that. This is not things that we want to be sure we don't make any mistakes. So 13 times 19 is 247. Hey, if I do a mistake, please stop me, no? Don't let me go. And at the end, we realize that we have a problem. Okay, we need to compute phi. What is the name of phi? Totient. We need to compute the totient. So what is the totient? We subtract 1 to the first prime number, we subtract 1 to the second prime number, and we multiply them. So 13 minus 1 will be what? 12. Time Q minus 1, 19 minus 1, 18. So the result will be, where is my calculator? It is there. So 12 times 18. 216. So now we need to choose E. What is E? What is the name of E? The public exponent. How can we choose E? What is the condition to choose E? It has to be prime, coprime with 216. So they cannot share divisor. So maybe before I do that, we can write 216 as a product of prime number. 216 is equal what? 2 times 108, isn't it? So it's 2 times 2 times 54, isn't it? It's 2 times 2 times 2, 27. So it's what? 2, well, let me put 2 to the 3. And 27 is what? 3 times 9. And 9 is 3 times 3. So at the end, this is 2 to the power of 3 times 3 to the power of 3. Okay, it's 8 times 9. Is it okay? So give me an example of the public exponent. Let's see. Can I choose 2 for the public exponent? No, because 2 will divide both. Can I choose 3? No, because 3 will divide both. Can I choose 4? No, because 4 and 2 will divide both. Can I choose 5? Yes, they will be coprime. The only divisor will be 1. Can I choose 6? No. Can I choose 7? Yes. Can I choose 8? No. Can I choose 9? No. Can I choose 10? No. Because 2 divide 10 and 2 divide 2, 16. So I can choose, for example, we say 5, we say 7. Let me see here, which is 5. So let me choose, for example, 5. I never say that you have to choose 5. You can choose 7. So it's why I tell you there are several public key and several private key, because you have some flexibility to choose E. Okay, so now we need to compute the private exponent, which is called D. So to choose the private exponent, there is one equation that E and D must fulfill. What is this equation? When I multiply the public exponent with the private exponent, it has to be congruent to 1 modulus the totient. Modulus the totient. So it has to be 1 modulus 216. Since we choose E as 5, I have to resolve 5 times D, I have to find D, such as 5 times D is equal to 1 modulus 216. So these have a solution. Why we know that these have a solution? If 5 and 216 are coprime, I did choose them as coprime. That was one of the conditions to choose E. We know that there exists a multiplicative inverse, modulus 216. So it does exist. So to find it, there are several ways. I can make a small program that will find it for me. Or I can do what we saw previously. So we can try to express 216 in function of 5. So 216 will be 5 times something. Okay, let's see. 216 divided by 5 will be 43. So it's 5 times 43. And 5 times 43 will be 215 plus 1. I'm already done. Here I don't need to go further away because I already have plus 1. Okay? So I can just say, oh, I already find 1. So I can say what? That 216 minus 5 times 43 is equal to 1. So now I can also say what? That it will be also true if I apply this to modulus 216. Will be 1 modulus 216. So when I do something modulus 216, this is 216 times 1. I can suppress it. Or I can add. So you can suppress any things like 216 times a value. Or you can add any time 216 times a value. So for example, I can suppress this. So I can say it's the same thing as, let's put 5 times negative 43 is congruent to 1 modulus 216. So here what I did, there were 216 times 1, I make it disappear. This 216 times 1, I make it disappear. But I can add also 216 times something. So what about if we add 216 times 5? So I'm going to add 5 times 216. 216 times 5, I can add it. Plus 5 times negative 43 is congruent to 1 modulus 216. So if I factorize the 5, I will have 5 times 216 minus 43 is congruent to 1 modulus 216. And this will be what? 5 times, Okay, let's do 216 minus 43. 216 minus 43 is 173. So remember that the public exponent E, we choose it as 5. So this will be what? The private exponent, D. Let's verify that we don't have any problem. So look, 5 times, do I have the modulus here? Yeah. No, I don't have the modulus. Let me change the calculator. I do have the modulus. So 5 times 173 is equal modulus 216. It has to be 1. It is 1, as you can see. So it is congruent to 1 modulus 216. Perfect. So what will be my private key and what will be my public key? So the public key is a pair of integer, the public exponent and the modulus. So the public exponent, we choose it as 5, and the modulus, which was the product of the two integer, modulus is 247. So 5, 247. What is the private key? It will be the private exponent. We find it as the multiplicative inverse of 5 modulus 216 and the modulus. So it will be 173 and 247. Okay, so now let's try. So let's say that we have m. What are the possible value of m? M can be where? M can be any value between what and what? Any value between 0 inclusive and n, which is the modulus, 247. So m can be any value between 0 and 246, both inclusive. But you cannot choose m as 500. No. Have to be between 0 and n. 0 inclusive and n exclusive. So for example, I can choose 100. Or let's choose 104. So let's see what will be the ciphertext. So how do we compute the ciphertext? M to the power public exponents modulus n. Let's replace. M, which is the clear text or the plain text, is 104. Modulus E, modulus the public exponent, modulus 5, no, power 5, power E, modulus N, 247. So, well, I do need the help of a calculator. I better go to Python, which is an infinite precision calculator, no? Because those numbers can be very big. So 104 to the power of 5, which is 104 times 104 times 104, 5 times. Okay, let me do this. This result, modulus 247, 130. So it's giving me 130. So encrypting the integer 104 will give us the cipher integer 130. Let's do now that we start from 130 and want to come back to 104. So let's say that I receive this 130 and I want to come back to this 104. So the ciphertext is 130. How do I compute the plain text? It will be the ciphertext elevated to the private exponents modulus the modulus. So I just replace 130 to the power of D. What is D? D is a big integer, no? D was 173. You see it here? D is 173. So to the power 173 modulus 247. So these have to be 104. So let's ask Python to do that for us because we might take some time to compute that, no? 130 to the power 173. So let's ask our friend to do it for us. 130 to the power 173. Look at the integer. Doesn't fit in one line. It's fit in 4 lines, as you can see, no? But Python is an infinite precision calculator. So this, I'm going to do modulus 247, and it should be 104. Look at the result, 104. So we came back to 104. So equal 104. And this is exactly what we need. So any plain text, which is an integer between 0 inclusive and 246 inclusive that you encrypt, will give you a ciphertext that is also between 0 inclusive and 246 inclusive. And when you decrypt, of course, you will come back to the original integer. Do you have any question about it, or is it clear? Okay. Let's do a second exercise. In the slides, we have a second exercise. So here, they take 47 and 163. So P, the first prime number, is 47, and Q is 163. Let's verify. Yeah. So first, we need to show that 47 is a prime number. Of course, if they give it to us, it's a prime number. What are the prime numbers that you know? Let's put a list here. 2 is the first one, no? 3 is the second one. Then you have 5, then 7, 8 is not, 9 is not, 10 is not, 11 is prime number, 12 is not, 13 is prime number, 14 is not, 15 is not, 16 is not, 17 is a prime number, 18 is not, 19 is a prime number, 20, 21, 22 are not, 23 is a prime number, 24 is not, 25 is not, 26 is not, 27 is not, 28 is not, 29 is a prime number, blah, 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 blah. How can I show that 47 is not a prime number? If I ask you to show that 47 is not a prime number, you start dividing 47 with 2. If it gives you an exact division, it means that it's not prime. So we might do it just as a reminder, no? 47 divided by 2, give me some decimal, so it doesn't work. 47 divided by 3, no. 47, of course, 47 is not possible to divide by 5, because something that will divisible by 5 will end with 0, 5. 47 divided by 7 doesn't work neither. 47 divided by 11, the closest is 44. Does not work neither. Okay, we need to go up to square root of 47. So we don't need to go, I think I went further away, but we need to try up to 6. So we should have tried 2, 3, and 5. For example, for 167, it's not 167, it's 63, sorry. The square root is, we have to go up to 11. Try this integer to show that 2 does not divide it, 3 does not divide it, 5 does not divide it, 7 and 11. And that's it. We don't have to go further away. We have to go up to the square root of the number. Okay, so they are prime number. So let's proceed. What should I do first? Help me, please. So I need to compute the modulus. The modulus n. N is the first prime number times the second prime number. So 43 times 163. So 43 times 163 is 7,009. Oh, thank you. You see, if you don't tell me, we go very bad, then I lose a bunch of time, then I realize, oh, there is something that we did wrong. It's 47 times 163. So it's getting me 7,661. 7,661. Now we need phi, the totient. So the totient will be P minus 1 times Q minus 1. So 47 minus 1 will be 46 times 163 minus 1 will be 162. So we take the calculator and ask how much is 46 times 162. 7,452. So 7,452. Okay? So now, what is the next step? We need to choose E, the public exponent, such as what? Any integer that will be co-prime with this one. So, for example, let me see my slide, the one that they choose here, so we can verify that we don't have problem. They choose 7. So, to be sure that it is co-prime, what should I do? It have to be co-prime with phi. I try to divide, because this is a prime number. So if 7 does not divide phi, it's okay. They are co-prime. So let me try. 7,452 divided by 7. Okay. Okay, it does not divide it. So they are co-prime. So now what should I resolve? I need to resolve this equation. The public exponent times the private exponent must be congruent to 1 modulus the totient. So the totient is 7,452. So I need to resolve this equation. I already have E. I choose E as 7. So what I need to resolve is 7 times D must be equal congruent to 1 modulus 7,452. Okay? So let's compute it, and then let's do a program that will compute it for us. So if we compute it, we need to express 7,452 in function of 7. So let me take my calculator. 7,452 divided by 7 is 1,064. So it will be 7 times 1,064 plus something. How do I compute this something here with the calculator? I can do 7,452 modulus 7, and it's 74. Okay? Now I need to express 7 in function of 5. So 7 in function of 4, sorry. So 7 is 4 times 1 plus 3. Now I need to express 4 in function of 3. So 4 is 3 times 1 plus 1. And here, bingo, we got the 1. We can stop. Because look at what we have to resolve. It includes a 1. So I need a 1. I found the one that I need. So we can stop and go back. So what can we say? We can say that from here, we can say that 1 is 4 minus 3 times 1. Now we have 3 here. We can get 3. What is 3 from that? 3 is 7 minus 4, isn't it? According to that. So I'm going to replace these 3 with these 3. So 1 is equal to 4 minus 3, which is 7 minus 4 times 1. I should not even write times 1. So 1 is 4 minus 7 plus 4. So I put the 4 together and the 7 together. So it will be 4 times 2 minus 7. Now we are going to take advantage of this one and replace the 4. So 4 will be, it's a little 74, 52. So look at the 4 here. 74, 52. What else? So the 4 here is 74, 52 minus 7 times 1064. Okay? So minus 7 times 1064. Minus 7. Oh, times 2 minus 7. No? Because we replace the 4 with this. Times 2 minus 7. So let's develop this. It will give me 7452 times 2 minus 7. So this number times 2 will be 2000. So I will have 8 here. I will have a 2. 2128 minus 7. Do you agree with me? If I take 1064 times 2, give me 2128. So let's put the 7 together and the 7452 together. So it will give me 7452 times 2 and the 7 together. So minus 7 times 2129, isn't it? So 1 should be that. Let's verify it to be sure that we didn't make any mistake. So if I do 7452 times 2 minus 7 times 2129, let's give me 1. Bingo. We didn't make any mistake. So remember what we want to resolve. The public exponent is 7. And the totient is 7452. So the public exponent is 7. So if we have that, I can write it the other way also. So I can write 7452 times 2 minus 7 times 2129 is equal to 1. So if I do it modulus 7452, it will also work. So remember, when we do modulus 7452, we can make 7452 times something disappear. So I can make it disappear. I'm going to make it disappear. So it will be the same thing as, for example, 7 times negative 2129 is congruent to 1 modulus 7452. Is it okay for everybody? So the way that I make this disappear, I can also add. What about if I add 7 times 7452 7452. So I can make them disappear, or I can make them appear. Plus 7 times minus 2129 will be congruent to 1 modulus 7452. So if I factorize the 7 times 7452 minus 2129. 1 modulus 7452. So this will be 7 times, let's take the calculator. 7452 minus 2129 will give me 5323. So they are inverse to each other. Modulus 7452. So remember, this is E, the public exponent. So this will be D, the private exponent. So let's verify that we didn't make any mistake. 7 times 5323 equal modulus 7452 must be 1. Good. So they are inverse to each other, modulus 452. So what can I say? What is my public key? It will be a pair of integer that will have E, and that will have not, this is phi, the totient. It's not the totient, is what? Is the modulus. So where is the modulus? We compute the modulus at one point, which was P times Q. You see, you don't help me, no? You could have said the modulus is 7,661. So 7,661. This will be the public key. What will be the private key? So this is the public key, and the private key will be 5,323, and the modulus, or n, which is 7,661. They are here. So let's use our computer to compute this 5,323. So I need to resolve this equation. 7 times the private key must be congruent to 1 modulus 7,452. Okay, let's do a Python program, or let's do a bash program to do that. So let me try to put that in a corner. What we want to resolve here, and here my okay, let's create a program. Let's inverse mode. The py, I create a file. I'm going to make the file executable, so the user have the execution rights. I'm going to edit the file. VI, it is called inverse mode.py. Okay, so the hash bang to say I'm using Python 3. Okay, so we want to solve this. 7 times D equal 1 modulus 7,452. So what shall we do? So we can start with a possible D. What is the minimum value of D? 2. So we are going to say while we are going to compute all of them, but the first one should be 5323. Then what will be the second one? We are going to find several. Okay, we will see how to compute them. So if what? If 7 times D modulus, let me put parentheses, it's going to be more clear for you. 7 times D modulus 7452 is equal to 1. This is a solution. So I'm going to put possible private exponent, and I'm going to show it. Possible private exponent, and I'm going to show it. Percentage D. And what should I do after that? I should increment D by 1 and try again. So this will loop forever. Look at how it's small. This will loop forever, but the first value that it will show is the one that we find, which is 5,323. So let's run that. And let's put, since it's going to show a bunch of them, if I forgot to close the parentheses here. Okay, look at them. Okay, so since it's a bunch, 5 less, look at the first. 5,323. How do I get this one? It will be 5,323 plus 7,452. How do I go from this one to this one? By step of 7,452. So let me open another shell and verify that. Let me say compute 5,322 plus 7,452. 7,452. XPR, sorry. It's getting me 12,775. How do I get the next one? I took 12,775 because it's modulus 7,452. So it's giving me 20,227, and I keep going like that. So 20,227 in 27,629. No, we could have just do a Python program so that as soon as I find the smaller one, I finish. So here, if I want to do that, I can put a break. We are done. We found it. Do it, and I finish. So if I run it, I don't need the less anymore. Here it is, the smaller one. So any D is okay. Any D that verify that. It doesn't mean that I have to choose this value. This is the smaller value. So I could have, instead of putting that, I could have put the second value or the third value. It will work also. Okay, so now that we have that, let's play a little encrypt and decrypt. So for example, Okay, we have the private and the public key here. Okay, so a plain text will be an integer between what and what? Any integer between what and what? Any integer that you take between 0 and 7,660, both inclusive, can be a plain text. So anyone that you want. So let's say that we take M. Which one you want to use? We are going to encrypt it, then we are going to decrypt it, and we have to come back to the original one. So which one do you want to use? Oh, 2004-77, for example. Okay. So it will be M to the power public exponent modulus N. So let me just replace 2477 modulus, the public exponent is 7. The power, the public exponent is 7. Modulus 7661. So let's compute that. Let's ask Python to compute that. That's too much for us. So 2477 to the power of 7. It's not a very big number. Modulus 7,661. So the ciphertext have to be in the same range, and it's 963. So 963. Now let's go back to see if it works. So if you give me the ciphertext and I need the plain text, I will do what? Ciphertext to the power of private exponent modulus N. So I will do 963 to the power of 5,323. 5,323 modulus 7,661. Of course, this number is going to be very large. So 963, which is the ciphertext, to the power 5,323. Let's just see how big it is. Okay, look at all the decimal, no? Wow, it's several pages. You see? I scroll, it's very big. But Python is not afraid of big number, as you can see. So we are going to say Python. By the way, I didn't need this parenthesis here. Do that, modulus 7,661, and we should come back to 2,477. As you can see, 2,477, we came back. Any integer that you do should go and come back without problem, because there is a mathematical theory that our friend from mathematics did for us. We just program it and we believe in what they say because they know what they say. Okay, so it was 2477. It did work. Okay, so that's it. Let's continue with the slides. That was just 2 exercises here. So they were saying encrypt this message. We could have encrypted. It's okay. So to compute x to the power of y modulus n, this can be tedious, of course. However, there is a way to do it much faster. So we are going to use a property of the modular arithmetic. And this property is the one that is there. If you want to compute A times B modulus N, you can first compute A modulus N on one side. On the other side, B modulus N. So you will get smaller number. You multiply the result modulus N, and that will be the same thing. So they ask you, for example, to compute that. This number, we will compute it. Of course, we can put it in Python, and Python will tell us with a problem. But we'll look at what they say. To do the previous exercises, these 3 exercises, you are not allowed to use an arbitrary precision calculator, such as BC or Python. So we cannot use BC, we cannot use Python. But you can use, for example, EXPR, which is much limited because it's work with integer up to 64 bits. Or for example, in the bash, we can put between $parenthesis parenthesis an expression and close it with parenthesis parenthesis, it will work. But the integer that we have to put here must be 64 bits, no bigger. So of course, this is much bigger than 64 bits. Okay, which means that the integer that we manage with EXPR and this are integer between this range. I can even show you, for example, let's see that EXPR is limited to that. If we try bigger integer, EXPR will not like them. So let me copy this integer and call EXPR. For example, doing this integer plus 1. Oh, this one manage bigger integer, so maybe 128. Mine up to 64. So let's see that. Python 3, 2 to the power of 127 minus 1. 2 to the power of 127 minus 1. So I think this EXPR manage integer of 128 bits. So let's see. I'm going to put this integer plus 1. Oh, this EXPR is better than mine. It looks like Infinite Calculator also. Is. Okay, mine, I don't know, it's the way it was compiled, maybe. Okay, so you cannot use the EXPR. You need to use this. So let me show you, for example, echo. You can use, for example, show me 12 plus 89. Show me 12 times 89. Okay, but let's see if this calculator is also limited here. If I ask this maximum number plus 1, okay, look, it put a negative number, and this is not true. Now, if I put a 6 here plus 1, I reach the maximum. But if I put plus 2, the result is negative, which means that it's overflow. So which means that the $parenthesis parenthesis manage up to this value that is there, no? So if we do a program that just use that, we are sure that we never use integer bigger than 64 bits. So first of all, how can we solve that by hand? I want to solve it by hand. Say that if you want to solve, for example, 5,193 to the power of 10 modulus 7661, 7,661. How can we do that? Okay. So what we need is to do, for example, some of them. Let's do the first one. 5,193 to the power of 0 is what? Is 1. And it will be congruent to 1 modulus 7,661. Now, if I put 5,193 to the power of 1, it will be the same 5,193 modulus 7,661. Now, if I put 5,193 square, so this with a 64 calculator, we can do it. So let me do it here. I want to do 5,193 square. Look at the result. But I don't want the square. I want the modulus 7,661, no? Sorry. Modulus 7,661. And there is a missing parenthesis because I add a parenthesis. Okay, it will be 529. So it will be 529. Okay? Then I'm going to do this one to the 4. If I want to do to the 4, what should I do? According to the property that we saw. What can I type here to do to the 4? Just type 529, the previous result, which was the square. And it's giving me 4,045. So 4,045 modulus 7,661. Now, if I want 5,193 to the 8, I can take this one, multiply it by itself, modulus 7,661, and it will give me the result. So I'm going to take the previous result, which is 4,045, multiply by itself, which is the square, modulus 7,661. This gives me 5,790 modulus 7,661. Yeah, with that we can do this first one. So let's do the first one. So I need to do at the end to the power of 10. I need to do 5,193 to the power of 10. Modulus, I need to know what is the result of that. Modulus 7,661. So what can I say? That 10 is 8 plus 2, isn't it? So it's the same, modulus 761. What can I say? This will be 8 times square, isn't it? All this modulus 761, 7,661, isn't it? Do you agree? So according to the property, I can do like that. Let me put square bracket here. 5,193 to the power of 8 modulus 7,661 time 5,193 square modulus 7,661 all modulus 70661. I can do that. So the first one, we compute it already. It is there, 5,790. You see it? This is the first term. So 5,790. So I can replace the first term by 5,790. Time, the second, is the square. We did compute it also. The square is 529. So times 529. All modulus 7661. So let's do that. Oh, let's do that with the calculator that we know that don't work with integers that are bigger than 64 bits. So we are going to do I'm going to do 5,790 times 529. It gives us 6,171. Now let's verify that with Python. So let me call Python 3, and we are going to ask it to compute 5,790 to the power of 10 to see how big is the integer. It's not big, but it's more than 64 bits. Modulus 7,661. 7,661. So there is a time, power 10. So it should be 900. According to that. So let me see. No, it's not. Nobody said it's 5193 that I should have put here. 5193. Okay, that was what we were trying to compute. Let me go back. 5190 to the power of 10. That was what we're trying to compute. So let me do it. And let's see the result that we got. Okay, 6,171. But you see, I never have big number in all my computation. Always keep the number small, because there is a way to keep the number small and to compute that. Because having for example, if you work in C, standard C will manage integer up to 128 bits. But those integers are much bigger. So if you want to do it in C, you will have to use an infinite precision library from C. It doesn't have it naturally. And with that, you can do it. Or you can do what we did. So since it's time, I let this exercise. I want you to create a script, a bash script that we call power module. And we will use it like that. If we want to do what we just did, so we will execute it like that. We'll put here 5,193 to the power of 10 modulus 7661. So that will be x to the power of y modulus the modulus that you want. And when I execute that, it have to do this number to the power of this number modulus this number. Okay, this is what we did. We did 7193 to the power of 10 modulus something, a third number. So look, if you need to do, for example, this, how do you proceed? you write 261 as a sum of power of 2. So 261 is 261. Yeah, 261 is what? Is 256 plus 5. So plus 4 plus 1. So you need the power of 4, we already have it. The power of 1, we already have it. And we have up to the power of 8. So you need to compute a little more. No, we have up to the power of 8. So you compute the power of 16, the power of 32, the power of 64, the power of 128, and the power of 256. When you have the power of 256, which is easy to obtain because it's just square. We just do square, as you have you seen. We can obtain the power of 256 to 261, sorry. We can obtain the power of 261. Okay, so this is, look, it's not complex. It's basic math, as you can see. Math modular. The thing is that we are using big numbers. And since we are using big number, we cannot do it by hand. It will take too much time. So it's at the end, it's a very basic thing that we are doing, no? So thanks to God in the course, we will not see deeper math. There is no much math. And all the math that we have been seeing is very basic. That's our XOR. That's our, for example, modulus. Since the beginning of the course, I showed you the modulus. We did review on the modulus. The modular arithmetic is very important in cryptography. They use it a lot. So, of course, I did have to make some review. Computing the inverse is a little more complex. Inverse modular something is a little more complex, but you can do a program like I did. I did a program that gave me the inverse. Of course, you need to know how by hand you will have to do it if they ask you to do it by hand. Because one thing is, I know the method to get it, so I can program it. And another thing is that, for example, I use a function. There are functions in Python for that. That gives you the modular, the inverse. For example, if you need the inverse, there are functions. In C++, all those languages have that. Okay, because this is something that we use a lot. Okay, I'm going to stop here. Let me tell you something. I have looked at the homework one. You need to make a big effort when you do a report. So I don't have time to talk about it today. I will talk about it in 2 days on Thursday. If you look when I give you a homework, look at the presentation. Very nice. All is beautiful. You cannot say it's not beautiful, it is. So of course, I need you also, when you do a report, you need to do a professional report. You are close to exit here. You will be an alumni maybe next semester. So of course, you are going to go to the professional world. You cannot do report as you sent me. I saw the report, and it's like you just entered to JSU. So you do need to improve your report. So we'll talk about the report in 2 days. And I need some people to volunteer so we can see their report together, not laugh at the report. That's not, we are not going to, we are not going to laugh at them. We are going to learn what to do, what is correct and what is not correct. So I recommend you to be volunteer. Okay, let's use my report and tell me what was wrong in my report and what was good. So I show you your report, what I think is good, what I think is not good. So you learn and other people also learn because we need other people to learn. Okay? So I see you in 2 days. Thank you.